The following podcast is sponsored by Structure Tech.
So the way I describe building science is it kind of lands kind of a nice little niche in between architecture, engineering, and that could be mechanical engineering and somewhat structural engineering, material science, and construction management.
Welcome, everybody. You're listening to Structure Talk, a Structure Tech presentation. My name is Bill Ulrich, alongside Tessa Murray and Ruben Saltzman, the wonderful cast at Structure Tech Home Inspections. And we're here to talk today. I'm very excited about this. Our special guest is Pat Huelman from the University of Minnesota. And we're going to be talking about building science and cold weather building and all kinds of different stuff. But let me take a second here and introduce Pat officially. Pat, can you tell us all about yourself, please?
Yeah, well, I work at the University of Minnesota. I essentially wear three hats. So land-grant institutions are known for research, teaching, and outreach. So one hat is I'm associate professor in bioproducts and biosystems engineering, where I teach building science. We have a building science program, curriculum there. I do research. My primary research for the last few years has been with the Department of Energy's Building America program. But my primary hat, if you will, primary function at the university is I work with the University of Minnesota Extension. And what that really is all about is pay most of my salary. And for that, I do applied research and education to the masses, taking what information we know about buildings and building performance, building science, and getting it out to people that can use that knowledge, generally focused on the building profession. Too many consumers out there to do that one at a time. So we've chosen to work with builders and subcontractors, suppliers to get that information out.
Outstanding.
And you do get that out to people. I mean, Pat, I met you, I don't remember when, but the first time I really got to sit through your teaching was when you taught an all-day seminar for us home inspectors several years ago. And we all just went, wow, we need more Pat. This guy's awesome. I mean, it was such good information. And your name has come up on our podcast. What do you guys think? Maybe about 73 times we've mentioned getting you on this podcast.
Yes.
We talk about you. Well, Tessa especially talks about you a lot. So we're glad to have you on the show.
Yeah.
Well, I'm glad to be here. This is fun.
Good. Tessa, why don't you go ahead and do full disclosure here and kind of give the background of how you know Pat.
Well, I know Pat. Everything I know about building science came from University of Minnesota and the building science program that's led by Pat. So I went to the University of Minnesota and graduated with a degree in residential building science and technology, which it was in the bioproducts, biosystems engineering department. I don't know what is it called now, Pat?
Just building science and technology. We've dropped the residential.
Okay. Building science and technology. And it's a pretty small program at the University of Minnesota, but took some amazing classes taught by Pat, which led me down this road of, home performance, energy efficiency, and doing home inspections today, and doing a lot of teaching and training for other inspectors and real estate agents and all of that. So I owe it to Pat to where I am today. So thank you, Pat.
You're more than welcome. You're an extension of my extension, right?
There we go. Yes.
It's fair to say then this is the mentor and the mentee. It's sort of like Luke Skywalker and is it Obi-Wan Kenobi? Is that the relationship that we're working with here?
Oh boy.
So Pat, tell me, you've been doing this a long time. How did you happen into building science? What was your background before? And I know there's some real pioneers in this, and I consider you to be one of the pioneers in building science. So tell me how you got into this business.
Somewhat accidental. I mean, there certainly wasn't a discipline or a field of study called building science when I was in college. So I took things like environmental design, environmental studies. I focused a lot of my undergraduate and graduate work in energy and energy efficiency, how buildings interact with their environment. And I took architecture and some engineering, some landscape architecture. So it was always around how buildings work. And in essence, that's what building science is. So I would say what you find is, while there are lots of building scientists, few were trained in that way. They just became building scientists due to their interest and their background in things like thermodynamics and moisture control in buildings, materials, whether it's wood or other materials. So the way I describe building science is it kind of lands kind of a nice little niche in between architecture, engineering, and that could be mechanical engineering and somewhat structural engineering, material science, and construction management. And so that's really where it's housed, and it's all about how buildings perform. In the US, building science has become kind of synonymous with heat, air, and moisture flows in buildings. We call HAM. And that's not necessarily true worldwide. In Europe, building science is called building physics, in fact, and has a much wider connotation, including sound transmission and light and fire, other life safety issues. In Canada, it has a little combination or flair of that, but it's referred to building science. And quite frankly, that's where kind of the discipline or thoughts kind of leading to where we are today in building science came from. So early pioneers in Canada, and there were certainly pioneers here in the United States too, in the 40s and 50s and 60s that really kind of launched the idea of building science, building performance. I started out looking at energy primarily, and then I realized all the things that happen when you make buildings energy efficient, some of them good, some of them not so good, whether that's moisture control or indoor air quality or other concerns. And so then we realized we had to take a holistic approach, systems approach. I mean, when I came up here in 1988, my interview presentation was the house as a system, and this was such a novel concept. They actually gave me the job.
Wow, that's so cool.
But anyway, we realized we needed something that was much more holistic in its approach, both from a physics perspective or science perspective, as well as engineering and application. And that's really what building science has become.
Very good. So where were you before?
So I was at Iowa State, and I worked for the energy extension program there. And I came out of school, my undergraduate degree focused on energy. I then went to work for the Energy Extension Service at Iowa State. And that started to broaden out into a couple other areas. I led the indoor radon project with a colleague there, looking at radon issues in Iowa at that time. I then started the Iowa Quality Housing Council, and it was really trying to work with builders to build towards high performance homes. This was in the 80s. Ventilation started becoming a very popular topic, rain screens, things like that, which we still talk about and struggle to get into the market today. But anyway, that's where I spent the time. And then I came to University of Minnesota in 1998 to join the Cold Climate Housing Center at that time. It's now we just call it the Cold Climate Housing Program.
So at some point, people in your industry realized we had to connect this idea of HAM with the actual boots on the ground constructing these houses. Was there an aha moment where we have to somehow get in the room and have a conversation with everybody, this holistic approach that you're talking about? Or how did that fall into place?
Well, I think there probably were little light bulbs along the way. I can't think of the big aha moment, but I was, like I said, I was trained, if you will, and thought in energy. I thought in BTUs and kilowatt hours. And as I designed a number of houses in the late 70s and early 80s, and you start to get patterns. We're starting to think about, well, ventilation has to be an important aspect of building houses that are much tighter, right? And then you would see it, whether it's window condensation or other issues, mold growth on top plates. So then when I came to University of Minnesota, I came in 1988 into the Department of Forest Products. Why there? Well, most of our houses were built out of wood. And lo and behold, wood, has certain moisture issues associated with it. And the houses that we were building were having more and more moisture problems. So my head spun, right around from energy focus to, well, let's think about how we manage moisture in these buildings, whether it's inside the structure or in the wall cavity or, up in the attic. And then very naturally out of that became a concern for indoor air quality. Like, okay, now we kind of got the shell thing figured out, of the enclosure, the envelope. We've got some of the other efficiency things sorted out. We've got ventilation now or moisture control in place, but we still didn't have the indoor air quality picture totally solved, if you will. And so that really drove then a whole nother round of, well, how do we build these high performance homes that provide high quality, comfortable space, but also healthy space or healthy indoor air.
Sure. What year would you assign to that transition?
The early 90s. I think
Okay.
what had happened was the 80s. Well, the energy crisis got me involved in this in the first place in the 70s.
Yep.
In the 80s, we started kind of exercising our control, if you will, on energy through better insulation and air sealing and some of that. And again, then the ventilation came right in behind there. But by the early 90s, we realized we were building some pretty decent structures in terms of insulation and air tightness, but they were inadequately ventilated. And so by 1991, I had started a group called the Residential Ventilation Task Force here in Minnesota to look at how we are going to bring ventilation into new construction in Minnesota. And I think it started to come into the code, and then we developed what's called the Residential Ventilation Standards Group. And by 1994, we had in place basically a pretty solid approach of how we're going to mechanically ventilate our houses in Minnesota. And then by 2000, that became a code minimum, if you will. Not saying it's perfectly done today, by the way, but the foundation is there and the fundamentals are in place. And certainly our houses do have some type of ventilation. It's just maybe not the best or the most sophisticated approach.
Does perfection and houses, can we use that in the same sentence? I mean, to a degree, you always have some variability that it's imperfect in some way or another, right?
Absolutely. Yeah. And so I think, the great chase of all of us, and certainly building scientists, everyone would think that we're trying to chase the perfect house. And really what we're trying to chase is an understanding of how houses work so that we can build better houses and we can build houses that have some forgiveness or tolerance. I use the term robust a lot. I like the idea of something that's robust. And so we're not trying to hit perfect. We're trying to hit something that's robust enough that it will provide a high level of efficiency, a high level of moisture control and building durability, reduced maintenance, long life of our building materials, and provide a healthy indoor environment for the occupant. So I think robust is a better strategy than perfection because, one, I don't think it's really possible, and two, in the end, it has to be implemented and executed by a whole lot of hands that aren't going to understand how to achieve that perfection.
Yeah, you can drop the directions. Perfect. It's just, does somebody read them and actually do what you say? I could ask a gazillion questions, Pat. Like, this would be the next 7 hours. I would not stop. I would just keep firing questions at you. But I don't want to monopolize this entire conversation. Tessa, Ruben, feel free to jump in here at any time. I think I'm fascinated. And so, Tessa, just raise your hand. Tell me when to shut up. But I'm fascinated by the change in materials from old growth to this engineered products. I sit next to a mill right now in International Falls that makes an engineered product that goes into a lot of houses built right. Buffalo board, we've seen it all over the place. And you talk about engineered materials and durability, and then you throw in this cocktail of moisture and all of that other stuff. It just seems like this is a math equation that has so many variables. How do you begin to isolate them and solve to make sure that you're not changing one thing to the detriment of the other?
Well, no, it's an excellent question. And clearly our building materials have changed. Clearly our wood building materials have changed, and they have moved a long ways from solid sawn old growth lumber. And we don't have that and can't raise enough of that. So we aren't going back there. We're going to use wood in a more efficient manner, let's say. In doing so, it has different properties. So it's back to kind of the material science, but then how does it apply to buildings? And lo and behold, it's just simply behaves different when it's pushed a bit, if you will, or exposed to too much moisture. So it comes back to, it's not a material problem, it's a moisture problem, right? So we have to manage moisture better. And so, very interesting. I mean, and that just became so evident in a lot of things. I just spent a long time on the phone with someone that has a mold problem in their home, and they kept trying to express to them, it's not a mold problem, it's a moisture problem. You've got to go after and find the moisture problem. Then you can clean up the mold and it's gone. So same thing would be true for the wood. We've just got to simply treat it better, understand its change, understand how that impacts its performance, and understand how we might have to treat it differently when we put it into the building. So I think we're going to see a lot more wood in buildings for a lot of really good reasons, but I also that the same fear, let's say CLT, cross-laminated timber, has become very popular. And it's using full solid sawn lumber, but put together in plates, if you will. And it makes sense. It's a renewable resource. It's a low energy input. It can be durable if treated properly, and we can sequester a bunch of carbon into our buildings. So it really comes back to me. It just says, yeah, we just need better building science to use the materials properly and put them in the right place where they can do the job, and train the trades to respect and treat the material and implement or execute it properly. So when I think about building performance, it's like you said, there's design. How does it get designed and specified? We don't do a good job of that. There's a lot of unknowns when that piece of paper gets turned over to the trades to do their work. And the second part is the execution. How does it get executed? And some of that's by training and old wisdoms, other things that come along, and that's not necessarily adequate with some of the new technologies or new materials or the new designs that are being used today. Sometimes also forget is occupant interaction and the occupant role and how the building's operated and maintained. So all three of those have to have, building science understanding and information and education built into them to end up with the high performing building that we want at the other end.
Ruben here,
ahead,
I gotta jump in for a quick second and ask you, because you said we're gonna be seeing a lot more wood in our buildings. And it's something I kind of joke with a lot when we're teaching classes about how newer buildings have a lot less wood just because we're not over engineering these anymore. So when you say we're gonna be seeing more wood, I assume what you mean is that we're not gonna be seeing more wood in the same building. You're just saying we're gonna be seeing more building with wood in general, right?
Right. Yeah. We're going to see more wood related products. I mean,
Okay.
people look at, the energy intensity of some of the alternatives, whether it be concrete or steel or whatever. And while they look attractive and they don't degrade the same way, they still have other issues, right? And they're expensive. Wood's relatively inexpensive material. So I'm just saying we're going to see more wood or wood fiber into our buildings for a lot of other factors and forces in the both economic and environmentally.
Just wanted to clarify. Very good.
Yeah.
Well, I got the mic just for a quick second. One other thing I got to ask you about. 10 minutes ago, you had mentioned changes in buildings right around like 91. There were some changes, or there was basically a standard that came out for ventilation. And I seem to see that's about when we started seeing air exchangers in homes, was right around that time. Can you just tell me what being required right then?
I want to back up and introduce a little concept or idea. I like to use the metaphor of the cliff. And what has happened over time is we've taken our houses and we've taken some of the robustness out. We haven't paid attention to certain things that are important, and we've moved these houses closer to the cliff. Now, the cliff is a metaphor for a failure. It could be a structural failure. Those aren't all that common. They happen where something literally falls over the cliff, if you will, or falls down. But this is more other performance metaphors, whether it's combustion, safety, and indoor air quality problem, a mold problem, the building enclosure is deteriorating, the attic is full of frost and mold, or we have ice dams that just simply overfloweth. So the cliff is a metaphor for this performance failure. And we've moving houses towards the cliff for quite a while. I mean, we started in the 60s and 70s and 80s, and by the 90s, we were awfully close. The other thing that happened in the 90s, of course, was a massive boom. You could build anything, you could sell anything for top dollar. And so we had a massive influx of houses and buildings at that era that maybe some things were missed in the design and or the execution. I always refer to as the X factor, the execution factor, but it was becoming apparent that ventilation was critical. So in 1991, the code started to make a nod to ventilation. And by 94, it basically said in the code, if you build a tighter house, thou shalt have ventilation, mechanical ventilation. And it kind of implied if you build a leaky enough house, you don't need one. Well, that's flawed building science, but that's what it said. Some of those houses I call, kind of tight is not all right, ended up being at the edge of the cliff. So by 2000, it was clearly recognized that we needed mechanical ventilation. But meanwhile, the market itself had gotten pretty good foothold on air-to-air heat exchangers. At that time, the term was used. Now we call them heat recovery ventilators, energy recovery ventilators. We had a strong market in place in Minnesota by 2000. In 2000, the code came in and said, you all have mechanical ventilation, but we're going to allow exhaust-only ventilation to continue. I even was supportive of that idea at the time, just so that we could get it instituted and accepted and codified, if you will. Well, unbeknownst to me, all heck broke loose. So I always say, good intentions sometimes don't go the way you think they might. And the market went to a lot of exhaust-only ventilation, and the market for air-to-air heat exchangers and heat recovery ventilators, et cetera, fell way off.
Pat, if I can just jump in for a quick second, I'm going to do what Bill always does and explain these terms that our listenership might not know. Because just so people understand, when we talk about exhaust-only ventilation, we're talking about like a bath fan that runs 24/7. And it's usually going to be, for a long time, Panasonic had the market cornered. They were all Panasonics because they'd make these fans that would run 24/7 and they'd be silent. You wouldn't even know what was going. And it'd be like what, like 40 CFM or something like that. It'd be a low
or higher in some cases.
Yeah. And sometimes you'd even see it in a hallway upstairs. It'd just be in a second floor hallway and it would run nonstop. That's what Pat's talking about for exhaust-only ventilation.
Right.
per
And
se.
so you're exhausting the air out of the building and you're relying on leakage somewhere for the fresh air to come in and replace it.
Yep.
And it does put the house under a slight negative pressure. That's how it sucks the air in, that it needs to replace that air with quote unquote fresh outside air. It's not the grandest system, but we had made sure that the houses had sealed combustion for the most part. The negative pressure wasn't going to cause a combustion problem. The code had started to adopt some radon resistant strategies or techniques in the appendix. So we felt like radon might, if it was a problem, could be mitigated easily. So there was some thought that this is going to be an okay interim strategy, but I think everybody knew sooner or later we had to move in a cold climate, quite frankly, that has a very hot, humid summer climate that sometimes we fail to address. We were going to have to move to more of a balanced heat recovery ventilation system. And then in 2015, the code said you will have balanced ventilation. So now we got away from the exhaust only side and it was going to be balanced, but heat recovery was not required. Well, the reality is balanced system with no heat recovery is kind of an oddity. It's you'd have to make it up as you go. And so clearly in 2015, the market for the energy recovery ventilators, heat recovery ventilators came back strong. And again, the market now is predominantly that type of balanced ventilation.
Okay, Pat, I have so many questions that I want to ask you, but one of them would be, what has been your favorite research subject over the years? Like what topic or what thing have you learned a lot from or has surprised you or that you just think is fascinating?
Well, I'll answer that in two parts to keep them kind of separate. The first one is just recognizing that the order matters. And so this idea of the cliff is kind of an important backdrop here. But then we realized, well, what order we do things matters. And so the order that the market chose was, well, let's chase energy first. And then that caused moisture problems. Well, then let's chase, water control and water management. And in doing both of those, we ended up with an air tightness problem, if you will. And then the air tightness, and I'm going to put quotes on air tightness problem, that caused us to need to start thinking about ventilation. And at one point, that wasn't methodical and thought out in that way. That's just how the market did it. But all of a sudden, that's an aha moment. Like, we're doing this backwards, folks. And people would ask questions about, well, I have an existing home and should I put ventilation in? I said, of course. That's where you start, always. So then when you realize if you ventilate first, and sealed combustion, of course, is in there, I should say. Combustion safety was, kind of the last thing we went after. But if you do combustion safety, then you do ventilation, and then you do air tightness, and then you provide water control, then you can insulate all you want, make your heart happy. It all worked. You've made no big steps towards the cliff and probably have made several steps away from the cliff. And so that order and that sequence was an aha moment that was really big for me.
Pat, it's so fascinating to hear you say that because big aha moment for you, but we are still trying to teach that to not only homeowners, but contractors and people that work in the energy world too.
Oh, totally. So, where did I learn it? I learned it in new construction, right? Bear in mind, I'm going to be delicate about how I say this, but there were a lot of things we did that we knew we shouldn't be doing, or we knew what the outcome would be. And we're trying to caution folks, be careful, right? But Joe Stiebrich said it once, and he said, the building industry is a discovery industry. They find problems through discovery, or discovery is how they see problems. And so they aren't going to fix a problem they don't see or haven't discovered yet. And so it was that's just how the world works. So we had to go through each of those 5 levels: combustion safety, ventilation, air tightness, moisture control, and insulation, in unfortunately, a series of events that we discovered didn't work well. And then we turned it around, went the other direction. And I said right away, well, we're going to do this again with our existing buildings, right? People are going to go out there and they're going to want to save energy, and they're going to put insulation, and they're going to want to, air seal their building because it'll save energy. And then they've got a moisture problem. Then they fix the moisture problem, and all of a sudden they got a ventilation problem, and then they have a combustion safety problem. And so why would we do that? And weatherization learned that lesson the hard way, and they realized they had to turn things around. I don't know they do exactly the sequences I had mentioned. And then all of a sudden that became a guide for, okay, before we take this step, where does it sit in the order of things, and will it move us towards a cliff? And again, I agree with you. It sounds so simple. It's not as simple as it sounds, and it certainly isn't universally understood or accepted.
That reminds me, when I worked for the insulation company, a home performance company for 5 years, one of the hardest things to explain to a homeowner was, okay, well, yes, we're going to improve the energy efficiency of your house. We're going to air seal the attic, blow in insulation, but first we need to replace your water heater that's atmospherically vented with a power vent water heater, and we're going to have to add some more ventilation in your bathrooms.
Yeah.
And people are like, what? I just hired you to blow in insulation. What are you?
Not at all what I hired you for.
Yeah, exactly. Yeah. You just
But
told me seal it up, and then you're going to tell me to turn on a fan. Like, come on.
Exactly. Yeah. So it really is looking at the house, holistically and how all these pieces fit together. There's a lack of understanding of that.
Yeah, the second answer to that question was really as I developed my understanding of moisture management, and building enclosure systems. The energy part was simple, right? Just insulation and air sealing. That was an easy part. Managing moisture across the building thermal envelope, whether it be liquid water or vapor, that was much trickier. And the next aha was this idea of the perfect wall. Again, this is a term that was popularized by Joe Stiebrick from Building Science Corporation. But he is really quick to give credit to the early Canadian work where they had developed this concept very early on in the 60s, and it was written about in their what's called the Canadian Building Digest, CBDs. But it kind of came around again, and we saw lots of different iterations of this. I mean, you see, we had a term called SEP-EDMS, and there was outsolation, and there was persist and perform, and you name it, all kinds of acronyms around this single concept. And the concept is this simple. You put the structure of the building inside where it will always be warm and dry condition. So what's the most important thing in your house? Your structure, right? That determines ultimately its life expectancy or lifespan. So you put that inside, and then we want to control four things. We want to control water, heat, air, vapor, and we call those the four control layers. And so we put the four control layers to control water, heat, air, and moisture on the outside of the structure. And then a really important piece here is we put on a cladding system, a roofing system, could be a foundation system that provides drainage and drying. And even under our slabs, right, we put a large layer of aggregate that provides drainage and drying. So if we wrap our structure with those four control layers and the ability to drain and dry, it's going to work every time, everywhere, every place, every climate zone. It is simply so simple.
It's the perfect house, the perfect wall.
Yeah, the perfect wall. Well, we can mess it up in design by specifying perhaps the wrong material in the wrong place, or have a sequence issue, or we could have trade issues that don't install things properly. But on paper, this works so well. And so that was a big professional aha for me. And that really started to drive my looking for how do we put together buildings differently, because all of our buildings have integrated the structure into the insulation, and then we put an air barrier on the inside or outside or both, and then we control vapor on the inside, of course, in the winter, but it has to be controlled in the summer. And then we end up with a window leak where the water's in the middle and has no opportunity to dry whatsoever, and we just messed up the whole thing. So that's why a lot of the work has really been driven by trying to find a building system that's relatively quick, easy, relatively inexpensive to do, that will provide a structure for the house, to hold up the roof and keep the snow, up and resist wind loads. And if you're someplace where you have seismic or whatever, that structure is intact. And then peel on the layers of the onion, the control layers on the outside, and then make sure you drain and dry. And it's just so elegant. The control layers and the change in the cladding approach or drainage for the foundation or venting systems for the attic or roof are more expensive. And so again, it drives it back to, can we come up with a better structural approach to our buildings that gives us the flexibility and the finances to put the right coat on the outside, the right set of controllers on the outside.
So Pat, have you built houses this way?
Yeah, absolutely. We have looked at a number of things. Big project that we've been working on now, basically 2000, was the idea of plate construction. So could we replace the stud framing with a panel or a plate, a diaphragm, if you will? So a lot of people are familiar with diaphragms that move load, like a floor diaphragm or a roof diaphragm that moves loads around and are structurally integral and supportive. And could the wall be done in a similar way? And obviously in the past, the walls were mostly to hold the roof up, and then we stiffened them for shear and wind. But could we use plates or a diaphragm to do that same work? And sure enough, yeah, you can. And you can build relatively thin walls, a couple inches thick, in this plate fashion that provide structure for gravity loads, wind loads, et cetera. So that was going to be then an entry point to build the structure different. And there's no other way to insulate that, of course, because there isn't the cavity. You would insulate on the outside. So we did several iterations of that starting in around the 2000s. And then by 2014, a company here, a developer, builder, and another company teamed up to build 7 of these houses. And that was then the impetus for us to get a DOE grant to basically study this system and validate it for the market, which we have done. We've just completed that report. And one of the critical elements, as you might suspect, is the structural behavior of this panel or plate design. And now we are just starting a second DOE project to basically get the structural engineering that we need to support the building system that we need to support the exterior control layers or the perfect wall.
Sounds like a pretty cool system.
That's fun. And there are hybrid versions of this. There's other ways to implement what I've just kind of suggested in terms of the perfect wall. There are ways we can use other building systems. We can even use stud framing, like 2x4 stud framing. There's no need to go more than that. And again, provide our structure in a maybe more typical or old-fashioned approach, and then put the controllers the outside. Only part of that is it does get thicker, and we can execute the idea of the perfect wall in just about any structural system that you can come up with.
Pat, I know you built your own house back in the 90s, right?
Yep.
If you were to build your own house now, would you use this panelized system?
I would either use the panelized system or a hybrid version of it that we've been working on. Yes, absolutely. I have the classic 2x6 wall that has, in fact, built right on the outside, International Falls, I'm sure, with several layers of house wrap for water management, as well as some vapor control that was necessary because I have polyethylene on the inside, which I haven't recommended since 1999. And yet it works beautifully in the winter. It struggles just a tad in the summer. It's not a failure. I'm not close to the edge of the cliff, but there are some issues that, in terms of summer moisture that just aren't managed the way I'd like. And more so, if I were to have a window leak or some kind of penetration, the wall simply wouldn't recover very quickly. So I'd absolutely move back to either a hybrid or a panelized approach with the exterior controllers.
So Pat, on a follow-up to the perfect wall system, is it necessary to have the engineered products to create that type of structure? And do those engineered products, they obviously give you the flexibility to make these large panels, correct?
So right now we're using OSB as our panel. That's not because it's the only approach. You could use plywood. It's just that the OSB is being made, in this case, it's a very highly engineered, industrial, high strength, high test OSB that's 1.8 inches thick and comes in panels that are 8 foot wide and 24 foot long. So it's really being done because of the availability of that at a very affordable price. But there could be other things that certainly could be used here. People worry about the OSB, like, oh, moisture, right? Danger, danger, danger. Well, it's on the inside of your house in no worse shape than your floor or your coffee table or your walls, right? And so it is in that sense, and it's protected by a very intense, intentional air and water vapor barrier, fully adhered membrane to the outdoors. Now, there are issues about off-gassing and some other things that come along with adhesives, and of course, we've paid attention to that, and you want to use a product that's very stable in that regard. But I talked about CLT. Well, what if somebody says, I don't want engineered lumber? I like real wood. You could put up a CLT wall. It'd be a little thicker, and it'd be all solid-on lumber with some glue, of course, between the pieces. It'd look gorgeous, and it'd work fabulous. It'd just be incredibly expensive.
Sure. And these superstructures, when you create a wall like this or a structure like this, I'm imagining an airplane that's like incredibly strong in the first position that you build it. But if you go start cutting holes in it and trying to expand or add on to this, are there issues with that later on if people want to increase the size of the building?
Sure. Yeah. And the plane is really a good example. We've referred to it, I called it plate-like or diaphragm-like, but it's really a monocoque construction. So if you think of a plane where you think of a race car that just went through the worst wreck in its life, and the cage is totally intact with a driver inside. That's essentially what this is all about. And yes, you do have to be careful where you put the penetrations, how you put the penetrations originally. And then certainly if somebody wants to retrofit it, they don't just go in and say, well, I want to put on an addition here and cut out a 8-foot tall by 12 or 16-foot piece of the wall and put on their addition. So yeah, there are certainly limitations engineering wise. And that's really what we're trying to understand better with our current project is how many times can we perforate this plate and still maintain the structural integrity that we need.
Funny story, Pat, I remember when I was doing some blower door testing on those panelized houses just to measure how airtight they were, and they were the tightest houses I've ever tested. I remember turning on the kitchen hood vent and just having the front door just slam shut behind me because they were just so airtight. You turn on that fan and it's trying to pull in replacement air from somewhere.
Yeah, there's another aha moment, right? So, I mean, to build houses of that tightness, I mean, these are tightest houses as a pool of houses, the tightest houses probably in the country. And interestingly enough, nobody was running around on the job site with caulk guns, foam guns, cans of foam, trying to achieve that, right? You know, we see builders out there today trying to hit 3 air changes per hour at 50. That's a inside term for tightness, or 2 air changes per hour. We believe a house probably should be closer to 1 air change per hour. And they're running around just going through all kinds of interesting exercises to try to achieve that. And then here's a building that just by nature, how it got built, is that. And it's half of that. It's a half air change per hour.
Yeah.
And so that's back to, can we be smarter about our design and our goals? And the goal is to be airtight, put these panels together with this fully adhered membrane, and I'll be darned, it's tight, except for what little bit of leaks we get at windows, and windows are in rooms where people are. Life is good, except there was an aha. Turn on the range hood, too much negative pressure. Turn on an exhaust-only ventilation system, would be too much negative pressure. So it had to be balanced mechanical ventilation. We had to provide makeup air for the range hood. The clothes dryer now is running for 3 or 4 or 5, 6 hours constant on the weekend, causing extreme negative pressure. So that introduced for us now an unintended consequence. It was predictable and predicted, quite frankly, but now we have to put in an intentional makeup air system. And so you talked about the homeowner that you're trying to sell insulation and air sealing to with a little ventilation fan. Now try to explain to somebody, well, we just built you a building and now you're going to buy this really expensive makeup air box because it's so tight. People have to be able to break apart the idea of the tightness of the structure and the air that's needed inside, whether it be for makeup air or for healthy indoor air. They're 2 separate things. And once you have an airtight structure, it's very easy to provide good quality ventilation. And it's very easy to provide makeup air because it's predictable.
As long as it's maintained properly, right?
Oh, there we go. That's the third leg, right? Design, execution, and operation. Yeah, and I think we are still failing to get our homeowners in a proper place for the operation side of this, unfortunately.
What possibly could go wrong? Pat, we could spend 20 hours of constant questions. There's so much to peel back here, but thank you. I mean, we kind of have to put a wrap on this episode because there's just, where else do you break in and say, okay, time out? But this has been fantastic. It's just, I wish every homeowner would sit down and listen to this and just try to understand how a house performs. And then the next time they have a friend or a dad or somebody who wants to help them fix their house, they say, no. We need the contractor who understands what Pat just said. And those are the only people who can work on my house.
House is a system.
House is a system. And here's the tough part, quite frankly. It is a system. And you touch something, it probably is going to affect something else. So your job isn't just to go in and say, oh, you need a bath fan, and say, I'll put that in for you for X amount of money. Your job is, if I put this bath fan in, what else could happen? And that's easy conceptually, right? You're going to create some negative pressure. You're going to have some air coming in, whatever. And it's probably not the end of the world. It probably didn't move you very close to the cliff. However, you do need to answer the question, what else could happen if I do this? And that's the trickier problem, to be real honest, especially in existing homes, is let's move that up to a range hood. They want a new kitchen. They're going to put in a range hood. Go, I know how to do that. And you go, well, are you going to make sure it's vented to the outside? Because that's the whole point, is to get rid of the gases and the particulates and odors and get them to the outdoors. Oh, of course, yeah. Okay, so now we have a vented range hood, and it's going to backdraft a water heater or a furnace or mess with your wood stove or your fireplace or whatever. oh, this is a bigger problem. This is something we should have anticipated and should have asked questions about. This one is going to move the house way far towards the cliff. And to me, that's the simple part, is making sure you ask the question. Where I feel bad is, while building science can tell you what things might happen, they can't tell you always to the degree of what will happen or how bad it will be or what that consequence might be. And to me, that's the whole point of testing. So now you say, aha, I got an idea here, but I don't know exactly how far towards a cliff it's going to move me. So what I need to do is test now and test later to see if there were any unintended consequences or reactions to my, one thing I did to the system that might be problematic or need to be addressed. And so I'll kind of close with that, but I think it's really important. And you can't just by a phone call or on a piece of paper just guess what those reactions or consequences might be and to what degree they will occur.
Thank you, Pat, so much. This is amazing information, and I hope everybody who owns a house will sit down and commit an hour and hear the words that you're saying. You are preserving their investment in their home by giving it more durability. Go ahead, Tess, sorry.
I was going to just end this with one question to Pat. Pat, would you buy a 1.5-story house to live in yourself?
I thought you were going to ask about that. That's a long answer, but I'll just say this. I love 1.5-story houses. They were built with a very intentional purpose. They're incredibly material efficient. They had a lot of flexibility built into them, especially when we built them here with basements. Another whole question or series of things could come around
We'll talk about basements next time.
Yeah, but the point is, it was a marvelous design for the times. I think it even still has application today, but we certainly want to maintain the ones that we have. However, they were built in a time when energy was cheap, where people ran their indoor humidity at 15-20% in the winter, and that was it. And, the snow melted off the roof and ran down and was gone. I mean, we didn't have the ice dams as much there. And it worked, actually, from a lot of perspectives, but it wasn't efficient, maybe not durable either, because there still were ice dam issues and condensation issues on occasion. But we came in and tried to bring them up to a new standard, during the energy crisis and what we started to learn in the 80s and 90s. And that really is what pushed them over the edge, pushed them over the cliff. So it's just a matter of coming back. And, if you take the principles, again, of sequence, and I should mention that sequence again, because I think I misspoke one time, but take care of combustion safety, then ventilation, then water control, then air tightness, and then insulation. If you follow the sequence, you can do this safely. Then the second piece is think about the control layers. And when you get done, that roof has to have the 4 control layers: water control, which is the roof primarily, and then it has to have thermal insulation, an air barrier, vapor protection, and it has to have, remember, the cladding system that can drain and dry. So it has to be a ventilated roof system that will provide that relief or drainage and dryness should there ever be a moisture problem in the assembly. Can we do that on a 1.5-story? Absolutely.
I think you've got a paper that tells you exactly how to do it, right, Matt?
We do. Yeah, we call it Project Overcoat. It is slick. Really ends up being a hybrid, not a pure perfect roof, but it works. Yeah, it's not for the faint of heart. It's not for the person who's looking for the cheapest bid, but it absolutely works. It brings that 1.5-story house from the 50s through all the oopses and misery and puts it in the next century.
Awesome. See, my favorite house lives on forever. Thank you, Pat. Thank you for saving 1.5-story houses in urban centers all across this country. We really appreciate that. So
I would buy one, but I picked the right one that hasn't been messed up yet and that I can actually implement the overcoat on.
All right. Thank you, Pat. I've got to put a wrap on this. You've been listening to Structure Talk, a Structure Tech presentation. We will catch you next time. Thanks for listening.
For more information on how we can provide you with the right information about your home before you buy or sell, contact us at structuretech1.com.